Good morning. Kind of sorry I'm not with you this morning, but it's always been my dream to go see the total solar eclipse, and the next one doesn't happen in the US till I'm 70. So this is my shot. Um, want to go through the 8485 notes with you, and this at least will help me probably not get too sidetracked on other things. And then once we're done with that, you have a project to work on, and I'll talk more about the project in the video. So here's what we're doing: 8485 global climate change. There should be a note sheet that goes along with it, and I just made that so there's less writing, so I'll have to be looking over on the side to see what exactly is in it. But here's kind of where we're going. So how has the Earth's climate changed over time, and what evidence do scientists use to infer these changes? So we're kind of looking at evidence to support climate change, our changing climate. So number one we have is, how do we get ancient climate data? Thermometers recorded history has only been around for so long. How do we get it? You'll notice some of the slides have these links down at the bottom. Those are really interesting. They go to the websites where the pictures come from, where the information comes from. So if you don't fully understand it, you could go and read a ton more if you find it interesting, or if you think it's a bunch of hullabaloo, you could go read more. It's actually really quite interesting stuff. All right, so this first one is gases trapped in ice cores. We talked about glaciers before, how glaciers come when more snow falls and what melts. Well, as that snow is falling, the air that's in the atmosphere gets trapped inside the molecules. And as that gets compacted into ice, we get these tiny little air bubbles. And we're able to go back and look at those bubbles after we count down how many layers they are. We know how old it is. We can figure out all kinds of cool stuff. All right, so how are they helpful? Air bubbles. They're samples of ancient atmosphere greenhouse gas concentrations. So samples of sulfurite is the ancient atmosphere greenhouse gas concentrations. And the next thing, element isotopes and greenhouse gases help indicate temperatures. So we're going to come back a little bit more to that. There's this confusing graph I'm going to explain. It'll make more sense then. So help indicate temperatures from that one. And then last but not least on this slide, melt layers confirm periods of warmer temperatures. We talked about how in the summer that top part of the snow melts, and based on the warmer temperatures you can see, okay, yep, it's supposed to be warmer because of these isotopes, but that also fits with a thicker kind of melted band as opposed to the fluffier, more wintertime thing. All right, moving on. Letter B, tree rings. So tree rings, they indicate environmental and climate conditions for hundreds or thousands of years. So if you'd be the hundreds to thousands of years, because trees don't live beyond that, so it's hard to go further than that. But Methuselah, so this is a pine tree in California, it's almost 5,000 years old. So they don't have to cut the tree down to figure that out. Instead, they drill a core sample. So they try to aim right through the middle of the tree and carefully take out like a plug, and then you can from that count the rings while the tree's still alive. Pretty cool. All right, ocean sediments. So for these, varieties and concentrations of certain microorganisms in sediments record past changes in ocean temperature and composition. So past would be the changes in ocean temperature and composition. So microorganisms, they're going to live at different temperatures. So if we find them in an area now, we know what temperature they're going to live in. And then if we find them in a different area in these fossils, we know, okay, that area when this layer was made, it was that temperature. All right, moving on then from ocean sediments. Coral reefs. This one, when we get to the bottom of the page, is going to have a link. It's worth checking out. It's pretty cool. This here is actually an X-ray of some coral, and you can see how corals get bands in them or rings just like trees do. And from that, then, you can figure out all kinds of things about it. All right, so where are we? So varieties and concentrations. Oh, totally lost where I am. D. So bands in coral shell can change in thickness with changes in temperature, water clarity, or nutrient availability. And there's the link that I was talking about. I thought it was really pretty interesting. But it's kind of like tree rings in a way, but for coral reefs. And the next one, sedimentary rock layers. So color, type, and thickness of rock layers depend on, so it'd be the environment at the time they were deposited. And I didn't write all of this stuff down. So I would just focus on, depend on the environment at the time they were deposited. And while you write that, I'll blab a little bit, or at least read this. So till rocks indicate glacial formations. So where the glaciers come down and like break off pieces of the rock below them. So then you'll know where the glaciers were. Or desert rocks often have a distinctive red color. If you've been to the American Southwest, you'll see that. Rapid ocean evaporation and higher temperatures leave salt deposits. And so you can tell kind of what was going on based on what type of rock you have and what the layers look like. All right, key. So this is what goes up that left side of your paper, but we're finding that there's many sources of evidence point to the same thing. So if we were to just look at like the rock layers, that tells us one thing. But when they tell us the same thing that the coral tells us, which tells us the same thing as the trees, which tells us the same thing as the gases and the glaciers, well, we can take and piece all these together and say, okay, if we go back 1,000 years, what do all of these tell us? If they all start to match up, that it's saying it's a certain temperature, well then, it probably was that temperature. Okay, so now this isn't the graph that you have in your notes. Let me slide my notes up a little bit. I want to kind of look at some of these trends in graphs, and I made some notes to myself what to do. So this is a carbon dioxide graph, and you'll see I updated this morning with this red line the current level. I looked up what is it, and in 2024 right now we're at 420.62 parts per million. So if you take 1 million air molecules in the atmosphere, 420 of them, well 420.62 of them are going to be carbon dioxide. And going back 400,000 years, we've looked at carbon dioxide levels, largely from those glaciers, and we've never found them to be above this line. And you'll notice that not only are we past it, but we're going very rapidly past that, and higher still even. I think this was 2016, this graph. So 8 years we've gone up another one of these little bands. So industrialization, carbon dioxide levels have never been this high. And this kind of ties in with when did we start industrializing? When did we start burning fossil fuels? Okay, our next one, this is going to be a temperature anomaly graph. This is the one that you have, and you might even want to try to take and draw a horizontal line across here, because that's that 0 degree mark. What it's really looking at is it's looking at when was it above the temperature it is now. So this here, 0 degrees should be our temperature now. So in the past, when was it above that temperature, and when was it below that temperature? And the main thing to grab from this graph is if you have a horizontal line in there especially, you'll notice that almost in all of these last 800,000 years, it was cooler than what it is right now. We've had these very little time periods when we're higher than that. If I click a little bit further on, you'll see, okay, now I'm just looking at this very end part. And so kind of like, what does the little bit in here look like? So now instead of 800,000 years, we're just looking at 500 years. But in the last 500 years, we're jumping up much faster. This rate of increase here is much faster than what we've seen in the last 500 years. All right, this graph here is fairly confusing, but we'll go through it together. It's going to be good. All right, so if you look at the cycles and how they're linked, I'm going to start I think I start with my oxygen 18. Okay, so this oxygen 18, the second orange line from the bottom, this is going to be an isotope of oxygen. Normal oxygen is oxygen 16. Oxygen 18 is an isotope that's developed when you get more intense sunlight, you get more oxygen 18 concentrations. So this bottom orange line down here is insolation. You remember that's looking at how much sun's energy are we getting. So these little lines going across are trying to show you that, well, when we get higher insolation, when the sun is just in a more active, more intense period of time, it leads to higher oxygen 18 isotopes. So here the sun's energy is higher, more oxygen 18 follows right behind it. Sun's energy is less, you get less oxygen 18. And you get some of these going a little bit kind of funky backwards, but for the most part, even if you ignore the line, the oxygen 18 is going to be higher along with that. All right, I think that's what I wanted to say from there. Now, if we were to look at the others, so now when the insolation goes up, following those, these other ones also go up. So CH4, this is our methane. So when insulation goes up, oxygen 18 does, but also the amount of methane production, which we have more of the red, so the temperature also goes up, fits with the sun being more intense, and carbon dioxide also goes up. So, great graph. But the part that's concerning about the graph is if you just look at this last centimeter, and you'll notice in this last centimeter, our insulation levels are going down. Okay, that's good for us. You'll notice that the oxygen 18 levels are going down. Okay, that's also good for us. But now we notice something totally different, especially if you look past the end of the graph here, where we have our methane levels. Well, they should be going down just like the rest, and they were for a bit. But now you'll see the methane levels, it's way up here, that the methane levels have jumped up just a ton. And the temperature levels also, they should be going down. We're high, we're consistently high. We haven't been consistently high like that going back these 425,000 years. But also, last but not least, our carbon dioxide levels, we're off the chart. Oops, we are up to the very top of my picture. So where insulation is going down, oxygen 18 is going down, everything else should be going down. We'll notice methane, temperature, and carbon dioxide are not. Okay, then I'll play this. So this is looking at up to 2016, so 8 years ago. And the colors are going to give us the different temperatures. And these are looking at, I think, 4-year averages. So each snapshot is a 4-year average. And it's especially this very last part, you'll notice we get way more red. So the last, maybe when do we see the red really kicking in there? See if I can jump back here. So not in the 60s, okay, starting kind of in the 70s, especially in the 80s, 90s, 2000s especially. I think this kicks us over to the back side now of your notes. So summary, what's this ancient climate data revealing? So as Earth warms, let me flip over my page here too. Okay, so as Earth moved out of ice ages over the past million years, the global temperature rose a total of, so in your blank there, 4 to 7 degrees Celsius over the next 5,000 years. So you've had these series of ice ages throughout Earth's history that we can find, and every time temperature goes up 4 to 7 degrees Celsius when we come out of an ice age. So that's going to be about, so this is the next two blanks, the 0.08 to 0.14 degrees Celsius per 100 years. So if what we're seeing now is kind of a normal trend, we should see it going up 0.08 to 0.14 degrees Celsius every 100 years. Because one of the arguments is, well, every time we come out of an ice age, the temperature increases. And that's true. Okay. In the past century, so in the past 100 years, when we should be seeing these type of numbers, the temperature has climbed 0.7 degrees Celsius. So that's your next blank, the 0.7 degrees Celsius. So if we should be seeing this, we're seeing this, that is about 5 to 8 times faster than the average rate of warming. So it's warming like we could expect, but that warming is 5 to 8 times faster than what we should be expecting. Okay. So the next part, models predicting the warming for the next century of 2 to 6 degrees Celsius. So 100 years, it's been in the past 0.08 to 0.14. We've seen it 0.7 in our last 100 years. We think in our next 100 years we're looking at 2 to 6 degrees Celsius, which is 20 times faster than has ever been recorded before. So that next blank then is 20, as in 20 times faster than the last bit ever been recorded before. So that's kind of scary. It's 20 times faster than the last 100 years, which is 5 to 8 times faster than what we normally see. So we're seeing some pretty drastic, not before recorded changes. All right, 8.5. So jumping down to 8.5, we're looking at how do changing climate patterns affect the Earth.
2 degrees is the target for limiting the global temperature increase, but if greenhouse gas emissions were halted now, temperatures would still rise by up to 1 degree Celsius. 6,000 years ago, temperatures were at this level, and America's Midwest was a desert. The world's food production centres will become barren again. In this future, mountains lose their glaciers and rivers vanish, the Indian subcontinent fighting for survival. A single-degree temperature increase could eliminate fresh water from a third of the planet within 85 years. Warming at the poles happens faster than the global average. 40% of Arctic sea ice has disappeared in the last 30 years. While ice reflects heat, oceans absorb it. So as ice melts, the process becomes self-reinforcing. More ocean surface means more heat absorbed, which raises temperatures, making the ice less likely to reform. Mountainous regions are at greater risk of landslides as the permafrost which held them together for thousands of years melts away. Low-lying countries like the Maldives are submerged as sea levels rise, and countries already hit by hurricanes face ever greater storms. At a 2-degree rise, people begin to die in what are now considered normal summers. In 2003, with temperatures 2.3 degrees above average, 52,000 people died across Europe. Plant growth slows down, then stops. They don't absorb carbon dioxide as efficiently, instead emitting it. The extra carbon sees global warming spiral out of control. 125,000 years ago, when temperatures were 2 degrees higher, sea levels were up by 6 metres. Today, that extra water makes up our polar ice, which is melting. By the year 2100, sea levels could rise by a metre, displacing 10% of the world's population. In this 2-degree future, ecosystems across the globe collapse as species migrate and fall out of sync. A third of all life on Earth faces extinction. Scientists say we can still avoid a 2-degree rise if we limit our carbon emissions to no more than 2.9 trillion tonnes. We've already used 1.9 trillion tonnes. We have 1 trillion left to use between now and forever. At the current rate, we'll use it in just 21 years.
The situation in the Asian region in particular is extremely serious. Nearly all of the natural rainforest has gone from several countries now, Thailand and the Philippines, and what remains in the big blocks, for example in the Indonesian islands in New Guinea, is now under serious threat, not least because of the huge consumption boom that's going on in China.
We might know in our bones that that matters. But why? What, if anything, does wilderness actually do for us?
We're getting a better understanding today of how there are some basic life-supporting services that the planet provides. Fresh water is a classic example of that. That if we don't put an effort into conservation, we're not going to only make our lives worse, but it's also going to impact wildlife.
Is this radically new understanding enough to make us all think again? And why are the world's religions suddenly getting involved?
Wilderness always speaks to human beings of transcendence in the widest possible sense. It says you as a human being are part of a system which is not just about your needs and your concerns. Like it or not, you're part of something immense and very mysterious.
Immense, mysterious, and disappearing. Disappearing as human society expands, develops. But surely an aware society can learn to live sustainably.
The term sustainable development is a contradiction in terms we can have no kind of development. We've gone much too far. What we need is a sustainable retreat from the mess that we're now in.
Who's really going to go out there and pretend there isn't going to be development in human societies, development in our own evolution as a species, development in the way we help poor people to live better, more dignified lives? What kind of world is it in which there's going to be no development? Everything stops right now.
If you want to use these mountainous forests, for example, for the plantations to produce paper or to produce building materials, you can. But you do that at the risk of not having rivers flow and not having rainfall.
It seems to me that the issue of conservation of the natural world is something which can unite humanity if the people know enough about it, persuade them to change the way in which they behave, to change their view that gross materialism and the search of material wealth is not the only thing in life.
This is an opportunity for greatness which has never been offered to any civilization, any generation in any civilization in human history before, to act as a generation, to do the right thing. If we fail to receive that opportunity to act on it, then my feeling is we will become the most vilified generation that's ever lived in human history.
Quick comment about the video. One, the eyebrows. You can't miss the eyebrows. Two, the part that I think gets hard being a Christian in dealing with this is, one, God calls us to. It's in that fill the earth and subdue it. God calls us to take care of this world that he put us in, that he made for us to enjoy, but to take care of. And it gets a little bit awkward, I think, sometimes as Christians, because the video we watched before with Katherine Hayhoe, the climate scientist from Canada, is she said the number one predictor about your views on climate are the political party that you're in. And sometimes our views are so closely tied to our political party that it feels hard to deviate from that, because what is it saying about you? And it's sometimes hard for me as a teacher to talk about it, because then are you going to judge where am I and what political party am I in? And you don't know based on this, that God calls us all to take care of the environment. And the guy's comment at the end, or towards the end, is really kind of sticks with me about how we're the generation that knows about this. And if we choose to not do anything about it, we're going to become the most vilified generation in all of history. That's a lot. So some things to write from these videos. Number one, development hurts natural ecosystems, and I'm just going to record two ways. One, droughts. The woman talked about that. And wildlife extinction. And both of those are things that we're already seeing happening. Okay, so glacial retreat. Here's another video for you.
All the glaciers are shrinking. In the 1800s, there were estimated to be about 150 glaciers here. However, today we only have 25 glaciers. The glaciers are measured by a number of different ways. One of the most obvious ones is using repeat photography, where we go and occupy a site from which a photographer took a picture in, say, 1910, and then we re-photograph that from exactly the same spot. Once you go every several years to 5 years or 10 years, that's when you see the really big changes. When we first started this project, we thought every other year was going to be too much. But recently we've seen so much glacier change that now we are increasing our frequency of repeating photographs or visiting glaciers. You can see that it's all melted away, the lake has gotten bigger, all this ice has contributed to the water and is retreated back up towards the head wall of the mountain. We also do things that are a little bit more modern, such as taking precision global positioning systems and going along the margins of the ice so that we can look at changes in the area of the ice through time.
Glacier National Park is an excellent natural laboratory to examine the effects of climate change. This area is actually warming at 2 to 3 times the rate of the global average rise in air temperatures. So these increased air temperatures are decreasing the snowpack in the glaciers in the high country and increasing disturbance events like wildfires that we're experiencing.
Some of the species that we're studying, these aquatic insects, might be the first species actually to go extinct due to the effects of global climate change. We've already seen a contraction in the distribution of some of these species in comparison to collections that were done back in the 1960s.
Even though glaciers may seem disconnected and far away to people, they actually affect a lot of things downstream. And that's even evident in other things such as the way that the snowpack affects the huckleberry crop. And this is, of course, a vital food source for grizzly bears.
Animals that live in these upper elevations are adapted to the colder temperatures there, and because we're predicting warmer temperatures, they may be particularly vulnerable to these changes. They also have very specific food needs, and the food changes for them could also influence their ability to thrive.
in spite of the fact that it'll be different in the future, it's still going to be a valuable asset to Americans, both as a research outdoor laboratory and maybe as a kind of iconic lesson as to what climate change can do to natural landscapes.
Okay, so some stuff about the glacier retreat from the video. One, glaciers are shrinking. So lots and lots and lots of evidence for that. Water levels are rising. That snow, that solid water that was piled up on land, well, that's going down into the liquid water, and it's making things higher. Then temperatures in that area are rising more than surrounding areas. So temperatures in that area, so Glacier National Park in particular there, rising more than surrounding areas. And last but not least, animals and food chains are impacted. Right, next we have sea level rise. You'll notice the graph here goes from about probably 1993 up until probably about 2020. And it's gone up 80 millimeters, a little over that, so 8 centimeters in that amount of time. So things to write down, I'd write down the 3.2 millimeters per year, so 3.2 mm per year. And that's going to come from two things. One is going to be from glacier melt. We have this frozen water that's up on land. As that melts, that goes into the oceans. The other thing is going to be thermal expansion. And where as water gets warm, it gets a little bit less dense. It spreads out, which isn't much, but you take the depth of the ocean, a tiny bit of expansion multiplied by how much water there is there, it starts to add up. Next one, extreme weather. So natural disasters around the world. Higher ocean temperatures, which we're seeing, are going to give us more evaporation, which then is going to cause more extreme weather. So I would start by writing higher ocean temperatures cause more evaporation. So higher water temperatures cause more evaporation. And then that can change climate patterns and ocean currents. So can change climate patterns and ocean currents. And as we look at this graph here, you'll notice from 1980, the orange, the hydrological disasters, well, that orange band is a lot thicker. The meteorological, so things that are going on in the atmosphere, there is a lot more of those too. So the climate related, the purple, that's about twice as thick. The yellow even, the geophysical, so volcanic and tectonic activity, those are on the rise as well. I think on my next slide, maybe my last slide, is the graph that you have. Oh, nope, not quite to yours yet. But you'll notice areas exposed, so hurricanes are all the purple. Desertification, so things becoming way more arid, is yellow. The blues are small islands and deltas, places where the extreme weather, greater surf, water surge is going to be more and more of a problem. Some islands like the Maldives completely going underwater. Then maybe this next one, oh, I guess we're not quite up to there. So the graph that you have in your notes, I don't seem to have, but you'll notice the numbers at the top are looking at the number of extreme weather events, and those are going up as you go across. But also, well, I guess the cost is going kind of up and down. But it's a huge amount of cost. So 2016, that last year, $129 billion in economic problems from these things. Okay, so now you have time to work on your project. It's going to be due in the next class. And it's really an individual project, although the first part you'll start as a group. So based on the survey that you took after the test, I put people into categories. And actually, if I click here, so you should be able to find a link. I'm making this before you filled out the survey, but we'll have people kind of grouped together in some of these. And the thought would be the first few minutes, 5 minutes, maybe 10 minutes, kind of get together and just brainstorm together. So if you're like in the waterway group, all the waterway people get together and talk. I'm maybe a little ahead of myself. So here's the instructions that you'll find in Canvas. So it's saying, 1, conduct enough research to be an expert on how global climate change affects a particular category or sphere. Then back up claims with evidence or with relevant graphs and data. Present your information in an interesting way and inform the public in class. Next class, we're going to be giving a short summary of the final product, about a minute for each person. And then if people have questions, answer questions. So like I started to say, put all those waterway people together and just brainstorm. So I'll probably pull in like those whiteboards, or you could take a picture of it, what you come up with. We just kind of talk about how is climate change affecting waterways? What do we know about it? How is the temperature of the oceans changing? What about the level of the oceans changing? But you don't do the project as a group. You just talk for a few minutes. And then from there, we're going to break up. And now you pick like a subtopic. And this is what you're going to spend pretty much all of your time working on. So waterways, okay, how does that impact animals? So you could talk about fish, you could talk about coral, those are alive, but every person in your group has to pick a different topic. So one person might talk about coral, one person might talk about beluga whales, one person might talk about coastlines and things like that. Warning, make sure you're focusing on the impacts of climate change, not some other global issue. So pollution, maybe we should read the whole thing. You should be able to connect your issue back to increased greenhouse effect as the main cause. So the climate getting warmer. So not just pollution or short-term weather or something like that. Make sure it's a climate change related thing. Here is our rubric. So this here, you're probably all just going to get 2 points because I'm not here. But I'd encourage you 5 minutes, get together with the people in your bigger group, talk about it, and kind of decide what subgroups are you doing. Make sure that no one's overlapping with someone else. And then most of the rest of the hour, or all of the rest of the hour, then after those 5 minutes, you'll be working on this solo part here. And here's where the points are going to come from. And next class we'll be having the whole group get up together, and then just kind of one by one you go through and talk about your final project, and that's what this presentation is here. Make sure you look at these here. So 1 point comes from just don't read to us. So if you're making slides, don't read the slide. Have the slide be bullet points, know what you're going to say in advance and say it. Don't read it or I can't give you this point. You kept it to about a minute, so you don't have to say much. And 1 point, you seemed interested in what you were talking about. With what you have, though, make sure you don't have to necessarily show all of this to the class, but what you turn in to me, you should make sure you meet the criteria here in the rubric. All right, different things you could do. Most people just did a slideshow last year, but you could do infographics, you could do posters, you could write a persuasive essay, you could do any of these sorts of things. If you're doing like the speech, that would be something you'd record and turn in to me. It's separate from your 1 minute presentation. So you should have what you turn in to me, and you should probably in one big shared document have whatever you're going to click through for your 5 people in your 1 minute each sharing with the class. So just to make sure we're all on the same page. So 1, you're all doing something different inside your category. Make sure you don't overlap. 2, it has to be related to climate change, not just pollution or some environmental issue. 3, the thing that you turn into me should fit all of this green criteria. But you should have probably one shared slideshow for your group that you each have about 1 minute to share a portion of your material. All right, that's it. Hopefully it was all clear. Do the best you can, and we'll pick up the pieces when I return. Have a great day.